I don't really care about this wave function thing anyway. I'm just going to throw away the wave function, and I'm going to use something that's simpler, but that nonetheless describes everything about the system, right? And the classic method of that sort would be density functional theory. The advantage of these simpler descriptors is they lead to something that's computationally affordable. There's always some sort of good math that tells you that technically you haven't lost anything. And the sorts of examples here are things that you all have heard of: density functional theory, density matrix theories, electron propagator theory. These tend to work very well provided you know what you're doing. They aren't very robust. There are systems you should never try to describe with density functional theory, but might work with electron propagator theory. There are things you should never try to describe with normal electron propagator theory that might work with density functional theory. You sort of have to know the right method for the right problem. And once again, the most evil cases, things like the cuprates, things like these molecular magnets, you don't really have a right method for it, and you're stuck again, right? And there is, again, just like before, there's a hierarchy of methods. So you can get to the exact wave function by including higher order density matrices or higher order electron distribution functions, but they have the same scaling as the single reference methods. And therefore, once again, you can systematically approach the right answer, but at exponentially increasing cost. So the methods that my research group has mostly worked on, I should say, back when Juan was working with me, we were mostly doing density functional theory, but that's changed a little bit over the years, are what you would call direct assault. And direct assault sounds incredibly stupid because I told you that this is an exponentially complicated problem. But the idea is there must be some simplifying features of real electronic systems. There must be some way that we can approach them. Maybe we'll be creative enough to find some mathematical tricks that will let us actually look at these systems. One way is we could try to truncate the configuration interaction expansion. And this is something they do a lot in nuclear physics. It doesn't seem to be as useful in electronic structure theory, but more and more these days people are trying that approach. I'll tell you some results about factorizing the wave function, which you might think of just to sort of foreshadow that approach. It's like a generalized singular value decomposition. You could try to reparameterize the wave function. Think of something maybe better than single particle states to build up the wave function with. And you could try something like Monte Carlo techniques. All of these are direct assault methods, if you like. They basically are math tricks rather than physics or chemistry tricks. The catch is, once again, it's going to require us to use our brain in order to pick the right method for the right problem. So I'm going to have to introduce a little bit of second quantization in a physics audience. Hopefully this is just you becoming familiar with my notation specifically. But basically I'm going to use A's with pluses next to them to indicate the ways I create a single particle state, and I'll use A's without pluses on them, so the adjoint of those to be removing a single particle state. And the reason we do this is this allows us to keep track of the Pauli principle just using algebra. And it turns out that all of the essential methods we have that are very powerful in the direct assault method always are using the algebraic features of the wave function. Some of them use relatively simple Grassmann algebra like this. There are approaches that use much more sophisticated algebra, which I won't talk about today. Right? And so just to sort of give you an idea, if I want to create a Slater determinant, a single electron configuration, I just create an electron in the first single particle state, electron in the second single particle state, finally an electron in the nth single particle state. And I can do excitations by removing something from the reference and adding it to an unoccupied orbital, removing 2 electrons from the reference, adding to 2 unoccupied orbitals, and that will get me back a way of systematically expanding a reference state plus all the single excitations plus all the double excitations and so on. This would be a type 1 method, a conventional method where you take one electron configuration and correct it. We've already established this isn't going to work very well for our problems. Nonetheless, it's useful to sort of introduce the notation. To understand the methods that will work for our problems, you have to use something called the occupation number representation. So why do we need to do this? Remember I said we don't have a single electron configuration that we can use as a reference. If you don't have an electron configuration you can use as a reference, what that means is you shouldn't divide your orbitals into occupieds and unoccupied orbitals. You have to think of them all treated equivalently. Well, the only way I know to treat them equivalently is to stop building on top of some reference, but instead build directly from the vacuum. So I'm going to create electrons on top of the vacuum. This could be a pseudo vacuum, and sometimes will be, but in this talk it'll always be the physical vacuum. And what I'm going to do is say, well, if I put a creation operator here and I raise it to some power, if that power is 1, then you create, and because anything to the 0th power is 1, if you raise it to the 0th power, it just means multiply by 1 and nothing happens. And that allows me to rewrite a configuration interaction wave function by saying, well, I create on some basis set containing, in this case, k single particle states. I choose that they can be either created or just ignored. So all the occupations here are either 0 or 1. And then I make the sum of all of the number of occupied orbitals equal to the number of electrons. And if I sum over all the possible ways of picking n of the single particle states to operate, then that's all the possible electron configurations. Now, that sum, you can just really quickly count up, is going to have something on the order of 2 to the number of states in it. It's going to be exponentially complicated. This is not useful directly, but nonetheless, it's nice to be able to write down the exact wave function, and now we have to do our numerical tricks. Right? And to try to describe the numerical tricks, I'm going to use this sort of analogy. We have a bunch of people lined up here, and you can think of each of these as single particle states. The number of states of a person standing in line here ends up being exactly the same number as the number of states of a spatial basis function, right? Because each of these could pick up their right leg, they could pick up their left leg, or they could jump up and down, right? And that's exactly what you have, is you can have an upspin electron, you can have a downspin electron, or you can have an up and a downspin electron. And if this fellow on the end jumps, then the fellow next to him is going to feel that, and it's also going to have to jump a little bit. But this lady way on this end is going to be able to keep her feet nicely on the ground. And that's exactly the idea, is that the motion of this state and this state are correlated somehow, but a state is not very correlated to a state that's very far away. So there's a locality of electron configuration. It makes perfect sense when you think about it this way, that states that are close to each other are entangled and states that are far from each other are not entangled. Therefore, we don't need to sum over all the states, or rather there's some structure to it, right? Because not all these states are equally entangled with each other. Now the question is, can we somehow mimic this? And the basic idea is, well, why don't we rewrite this as some sort of factorized wave function? And so we would say, this fellow at the end, he's coupled to the fellow next to him, and he has some states. And then this fellow is coupled to the fellow at the end and this fellow. And so they have some shared indices that represent their coupling, right? And that's the basic idea here. Now, in order to actually go any further than people standing in a line, I actually have to do mathematics, right? There's no excuse at some point not to do it. And I'll try to make it as simple as I can. In fact, I'll try to make it even simpler than I really can. Everyone knows the idea of an eigenvalue decomposition. You just take some matrix and you say, well, I can rewrite it as a product of the eigenvectors and some number in the middle. And there's something that's a little bit less common for physicists called a Schmidt decomposition, which just means take the eigenvalues and wrap it into one of these vectors. And that lets you write a matrix as a product, as a sum of product of vectors, right? That's exactly the same sort of thing you would do in a singular value decomposition. And so if I only had 2 sites, I could do this Schmidt decomposition. I could say, well, what I really have is I have 2 choices, this coefficients, and they're just coupled together by a common index, right? So this is a sum of products of vectors to represent a matrix. Now, if I had 3 sites, then I would have vectors, and then I would have in the middle a vector that's coupled to the first one and a coupled to the last one. If I had 4, you would have, well, the 2 vectors and then 2 matrices in the middle that indicate the coupling. And that's exactly going back to this picture, is a state here is coupled to 2 things that are coupled to two things. And so you have vectors on the end and matrices in the middle. And when you come through this, you can factorize it in this form that has this entanglement. It says every state is entangled only to its neighboring two states. And they call this, for obvious reasons, a matrix product state, right? It's a product of matrices, just like a normal singular value decomposition is a sum of product of vectors. This is a sum of product of matrices. But notice now that this is exact. I haven't really changed anything, but there's an obvious thing I could change, which would be like a singular value decomposition in the same way that when you're doing this sort of Schmidt decomposition, you probably don't sum over all of them. You assume some of these vectors are small. Some of them are unimportant. We're going to do the same thing here, and we're going to say, no, we don't do the whole sum. We stop at some number of states, right? And this number of states we're just going to call D. We say, well, no matter how big, we don't let the matrices get so big. And by not letting the matrices go so big, we go from something like 2 to the number of states to a much smaller number, something like the number of states times the dimension of the matrix, of the number of elements of the matrix. And so now you no longer have exponential complexity. This is something that's going to be a lot cheaper, at least you hope so. Depends on how big D has to be, right? If D has to be on the order of 2 to the k, you have 1 nothing, right? And in practice, I mean, this is just showing you that you very quickly converge as you increase D. So you start with a relatively small value of D, and you keep increasing D, and at some point you can extrapolate to the right answer, the answer you would get if you did D equals infinity, right? So this is, if you like, a parameterization of the full CI wave function. It only has a polynomial number of unknowns. It's no longer exponentially complicated. There is sort of a hidden free factor. There's nothing I showed you. I showed you one example and said, it seems like you converge quickly with respect to D. There's nothing that says that will always be true. And in fact, it isn't always true. And a lot of very interesting systems, including my molecular magnet, D gets very, very big. D might be 100,000. But basically, the idea is you do some sort of singular value decomposition. And yeah, we've done some work. We actually have a code called KEMPS2 that if someone is interested in running the cyber calculation, they can use our program for doing it. So this is sort of the review of this. I don't know how politically correct this is. These are pictures from Catalan independence marches, right? And they, at one point, lined up Catalans, and they lined up all the way across Catalonia, and they decided they would make a statement. They didn't like, Madrid anymore, right? And this is exactly the sort of thing you can describe with the density matrix renormalization group. Every person is coupled to just 2 people. If it gets very hot in Catalonia, and I've been there, and one of the people faints, they'll take a couple people with them, but most of the chain will still be okay, right? Of course, this is, I mean, you're in Mexico and you know the Catalonians. And this is fine, and when they're doing political independence, this is what it's like. But this is what it's like when they're playing soccer, right? They beat Madrid. There's no order here. It's just chaos. And every person here is coupled to too many people. They are not coupled to 2 people anymore, right? And this sort of wave function is not going to work. There are methods that do work for this, right? And that's really where the research is going on. You could say, here the research is, can we build better software? Here the research is, can we describe things when a state is coupled to many other states, when there's strong entanglement that isn't very local? Speaking of strong entanglement, this will be a different approach. But imagine that you're trying to describe this sort of picture, and you could say that every person here you might think of as an electron. And suppose I would like to describe this lady. Well, the normal approximation we would do, this independent electron approximation, like you would do in Hartree-Fock or Kohn-Sham DFT, would be, well, I assume all of these people are moving independently. And it's going to be very, very hard to describe this motion if you pretend that these people are moving independently. So instead, you might say, but if you put this lady and this man together as a pair, they move relatively independently, right? Not perfectly. I mean, there's a little bit of correlation so they don't bump into other people, but the lady and the man are very tightly correlated, while the different couples are much more weakly correlated. And so at a chemical level, this makes a lot of sense. This is, again, first-year chemistry. We think of electron pairs, right? We think of electron pairs in physics, too. When you think about superconductors, you think about electron pairs. Sometimes a pair of electrons is the natural thing to be thinking about. And so why not no longer use one electron, single particle states? Why don't we use two electron states or two particle states? And that's an old idea. It goes back to Fock in the late 1940s, in fact, but those papers are in Russian. And so I'll cite the people who started working on it in the 1950s. And these two electron states, or in general two particle states, they're called geminals, like the Gemini twins, because you sort of have twins of particles together. And you could build up a wave function by creating geminals instead of creating orbitals. And that would be a different method. And as I said, there's a really long history of this sort of method, dating back to the early 1950s. In fact, dating back to my old PhD advisor in the mid-1950s. You might say, so this is an old idea. I've never heard anyone giving software for doing this. Well, there's a reason, which is that this idea tends to be really expensive. And to understand why it's really expensive, you need to just think about this wave function, and I've just plugged in the form of a geminal into this wave function. I say, so what if I wanted to compute the importance of an electron configuration, just the coefficient of an electron configuration? Well, it turns out I have a matrix here. It depends on the state, or the orbital I'm occupying, and the specific geminal, the specific electron pair I'm looking at. And the coefficient is something that they call a permanent. So it's like a determinant, but when you swap two rows, you don't get a minus sign. And in principle, that sounds like it should be better, because determinants are complicated, because you have to keep track of the phase, the minuses, and now you don't. But determinants are easy to evaluate, and permanents are essentially the definition of hard to evaluate, right? And the only thing that we could do then, realizing that, was also realize that there are a few special types of permanents. There aren't many, but here's one example, and it's a permanent that goes back to the 1850s, right? Where you can evaluate this really devilishly complicated problem, this thing that normally you could only calculate by just summing over n factorial permutations. But in this case, you rewrite it in terms of determinants, and determinants are ordering cubed, and you can actually deal with this permanent. And so there's a math trick, and then there's a physics trick, which is we don't solve h psi equals psi. We do what they call the weak form of the eigenvalue problem. We put a determinant on the other side of this, and then we say, well, if this equation is true, no matter what you put in the bra, then that's equivalent to solving the Schrodinger equation. And then we basically just solve for some specific states that we've put on the right side. So now I'm going to show you how this approach works. I'm going to start by giving you the carbon dimer. The carbon dimer is a terribly difficult system. This is, in fact, computed with the first method I told you about, this density matrix renormalization group using matrix product states. And I just compute the electronic spectrum. And you'll notice there's a lot of states here. It's not a single configuration problem. There's a lot of important states. And then I will actually show you the types of results we get with our method, which is quite close to the DMRG method. It's not exact, but it's actually pretty good. And the nice thing about this method is it costs the same as Concham DFT. And so you have a method that's very cheap. It basically is equivalent to evaluating some determinants, but nonetheless does the same sort of accuracy as a very accurate benchmark calculation. It costs the same as DFT, but the answers are much better. All of these curves were designed to dissociate to the same place. Here's the PPE functional. It will, somewhere around here, end up being the same, but basically shows you that a single electron method, or a single electron configuration method, is not a good idea when you have more than one important electron configuration. Here's a somewhat different example. Here's the Hubbard model. It works incredibly well in the strongly correlated limit. It's not great in the weakly correlated limit. That's something we understand. In this method, you do have to include the interactions between the pairs. It's still a starting point. And you have to, if you include the electrons, the interaction between the pairs, these numbers will get better also. the nice thing about it is it doesn't deteriorate as the system gets bigger, and you deal with the hardest part of the problem, which is the strongly correlated part of the Hubbard model, very, very accurately. And then finally, I will tell you that the one result that my postdocs were working on that really panicked me when they first did it. So everything we had tried was working well, and we did this uranium dioxide dication, and all of the methods we use were down here, except for the method that we believe is our best method, and it was way away from all the other ones. And we thought, oh no, we have finally broken our method, right? But then we looked at the experiment and realized, no, we're actually okay. It's that all the other methods are bad for this sort of system. Again, it's not a single reference system, and it's not a method that your normal methods will do well for. Okay? So with that, I'll conclude about this and say these geminal products are a different way of doing strong electron correlation. It's very fast. It's still a mean field method. It said that one electron, a single electron orbitals, you use 2 electron orbitals. There can be a hidden exponential prefactor. That's always true. Maybe this isn't the right. Maybe you don't have electron pairing. Maybe you have more complicated types of quasi-particles in your system. If so, you're going to have to do something different. But as long as you can build your wave function from electron pairs instead of quasi-independent electrons, this will work well. My take-home message, basically, is that if you think there's going to be more than one important electron configuration, that's essentially if your HOMO-LUMO gap, your band gap is small, then you should really think about other types of approaches, right? Whether you want to think about these sort of multi-reference, these matrix product states, whether you want to think about geminals, but whatever you do, somehow you have to include all the excitations. You can't stop with a single electron configuration. The other thing is that you may just choose to ignore the problem. I will admit, certainly in my research group, I think for most chemists, most of the time we ignore the problem and hope that the referee doesn't catch us. Right? That sort of is a standard approach, just because to get away from it is actually quite complicated. And I'll conclude by just advertising. So we have a software package we're writing together with Tom Verstralen and Ghent University in Belgium. And all of these methods end up getting implemented in the software package at some point. It's free, it's open source. If anyone's interested in it, by all means, just go and take a crack at it. Okay? With that, I'm finished. I'd be happy to answer any questions.
Están frente a la generación más antigua del grupo de física de estado sólido. Por lo menos habemos 3 aquí. Veo aquí a Rolando Jiménez y a Díaz Góngora. Me da mucho gusto no estar solo. Voy a presentarles mi trabajo. Dice así, lo voy a leer. Es un honor para mí el haber sido invitado a participar en este evento, organizado en ocasión de estarse celebrando el 50 aniversario del Grupo de Física del Estado Sólido de la Escuela de Física y Matemáticas. Un grupo emblemático y ejemplar, cuya formación no fue nada fácil. Antes bien, su estado actual muestra la visión, la tenacidad y la fortaleza de carácter de quienes participaron en su fundación, consolidación y franco desarrollo. Hay que retroceder hasta la primera mitad de los años 40 del siglo pasado para ubicar el primer gran esfuerzo por hacer física experimental en el Politécnico, de calidad académica, de clase mundial, como diríamos hoy día. Es Marietta Blau, la radiofísica austriaca, quien llegó a México en 1938 huyendo de la persecución nazi por recomendación de Albert Einstein al gobierno mexicano. Sus trabajos, publicados entre 1940 y 1944, en la revista Ciencia, Ingeniería y Revista Mexicana de Electricidad, llevados a cabo en solitario casi, muestran, por un lado, que en el Politécnico apenas se estaban construyendo las bases para el escalón siguiente, o sea, el posgrado y la investigación científica. Y por otro, no existían grupos grandes de estudiantes aspirando a entrar al mundo de la ciencia y la investigación. De manera que cuando ella tiene la posibilidad de ingresar a una universidad norteamericana, no duda en aceptar la propuesta y se va de México. Su partida significó el fin para aquel intento inicial, pero no el afán de impulsar el desarrollo científico del Politécnico. Ella estuvo en la CIME, por cierto, y en la época en que Sandoval Vallarta era el director general del Politécnico. Cerca de 20 años después de la etapa Blau, se funda en 1961 la Escuela Superior de Física y Matemáticas, y con ella, como instrumento, pronto se da un fuerte impulso a la ciencia en